This is lesson 4-7, understanding the relationship between equations and their graphs. We will start by going over the warm-up. And so on question number 1, the x-intercept is going to be -2, 0, and that's this point right there. The y-intercept is 0, -3, and that's this point. It is a decreasing function. The domain, as all exponential functions are, is from -infinity to infinity. Okay, the range, how low does it go? It's as low as, right here would be the asymptote, so that's going to be as low as -4, and it's going to go as high as infinity. If we're looking at the interval from -3 to 0, that's going to be from here to here, and so I'm looking at this point to this point, so I'm going to be looking at the slope right there. So I will be going down 7 and over 3, and that cannot be reduced, so that would be my slope, or the average rate of change for that interval. And then the equation of the asymptote is going to be y equals -4. Okay, the second question in the warm-up, the x-intercept right there is going to be 2, 0. Remember that for the x-intercept, y is always 0. The y-intercept is 0, -3. For the y-intercept, x is always 0. This is an increasing graph. As with all linear functions, the domain is from -infinity to infinity. The range, as with all linear functions, it is -infinity to infinity. If I'm looking at the interval from 0 to 4, so that's right here to right here, it doesn't actually matter with a linear equation because it's going to be the same rate of change no matter where you look because it's a constant rate of change. So I could probably look just right here, go up 3 and over 2, and then there are no asymptotes. Okay, with the lesson today we're going to talk about a lot of the same things that we've been doing, but we're going to add on the positive region of a function and the negative region of a function. Positive region is the part where it's above the x-axis. So if we look on this previous problem on your warm-up, this part of the graph is going to be positive, and this part of the graph will be negative because that's below the x-axis. So it all has to do with its relationship with the x-axis. At the point where the graph is neither positive or negative, it's the x-intercept. So again, on this previous example, this point right here that's the x-intercept, that would not be considered positive or negative. Okay, so let's do a few like this. So if we look at number 1, for each of the following graphs, we're going to do the same things we've been doing, state the x and y intercepts as an ordered pair. So let's go ahead and do that. So the x-intercept, okay, if you want to put a point on your paper, and that's going to be at the point 4, 0. The y-intercept is where it crosses the y-axis, and that's going to be 0, 7. Okay, B, state whether the function is increasing or decreasing. Since when we start at the left, it goes down, this is going to be a decreasing function. Okay, the domain is going to be, as with all linear equations, it's going to be all real numbers. So it's going to be x is an element of -infinity to infinity. And similarly with the range, all linear equations are -infinity to infinity because it goes down to -infinity and up to -infinity. Okay, I'm going to skip E for right now because that's the new part. And let's go to F. It says state the average rate of change for the interval, and so from 0 to 4. And we've already talked about how it doesn't really matter with a linear equation what interval you're talking about. It's going to be the same slope either way. But we're going to go down 7, and we're going to go over 4. So that's going to be my slope, or my rate of change for that interval. And then for G, write the equation of the asymptote, if any. Well, there isn't any, so we're going to write none. Okay, so now going back to E, this is the positive and negative part, and this is the new part. Sometimes it helps if you get a different color and highlight one or the other. So if I say this is my positive graph, and if I say that the purple is my negative, then that helps me a little bit. And just the same with the domain, where you take, somebody walking along the x-axis, as long as you're at negative infinity, your graph is in the positive part, because you would have to look up to see it. So I walk along, and it's still positive, still positive. So the positive part is as long as x is from negative infinity until it stops being negative at 4. So at this point right here, that's where it stops being negative. Then at this point, it stops being positive. It starts being negative here. So the negative is going to be as long as x is from 4, and then walk along till the rest of the time, so until you get to infinity. Now the reason why we are saying it's not inclusive, we're not doing square brackets, the reason why is because 4 itself is not positive or negative, so it's not included in either interval. So with the positive and negative parts, you're going to do similar to when you were talking about where's the domain and just thinking about walking along the x-axis, and it's positive from the time you get to from negative infinity until you get to this point, and then it's negative from that point until you get to infinity on this particular graph. Okay, for number 2, we can see that this is an exponential graph. So because of that, I do know what my domain is. I know that my domain is going to be from negative infinity to infinity, because all exponential equations have a domain of all real numbers. I like to kind of just do the easiest things first on these, but if you draw the asymptote here, that's going to help us because we have to do that for part G. We have to write the equation of the asymptote. So it's a horizontal line going through the y-axis, and it goes through the y-axis at -4. That's also directly related to the range, and so that's helpful, so that I know the lowest point of this graph is -4. So I'm going to say y is an element of the interval from -4, and then the highest is it goes to infinity. So that's how I'm going to start this problem, with just those easier problems. And then B, also, I can see that it's an increasing graph. And so those are the things that I would start with here. And then as the next things come along, I can just go back to part A and look at the y-intercept and x-intercept. So the x-intercept, where it crosses the x-axis, if I mark that, and if I mark the y-intercept, that's what I'm looking at. So the x-intercept, where it crosses the x-axis, is at 1, 0. You have to write that as an ordered pair. The y-intercept, where it crosses the y-axis, is at 0, -2. So with all x-intercepts, y is 0, and with all y-intercepts, x is 0. So that's something that's always true also. Okay, the next thing that I'm going to do, I'm going to skip down to part F, and that's going to be the interval from -1 to +2. And so if I go on my x-axis at -1, and I go on my x-axis at 2, and then if I just think about, I'm just looking at this part of the graph. So what I'm interested in is I'm interested in this piece from there to there, and I'm looking for what is the average rate of change from the first point to the second point. And so I'm going to be doing my rise over my run. And so I'm going to be starting here, and I'm going to be going up 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3. So I'm going to be doing up 7 and over 3, and so that's going to be my rate of change for that interval. Okay, the last thing I'm going to do is I'm going to do the positive and negative parts of this graph. And so as we've done, we're going to color the positive part. And so I'm going to color the positive part of this yellow, so that's for part D. And then I'm going to color the negative part of this green. I also like to color code over here, and so I don't get mixed up. So the positive part of this graph, I like to think about this as if you've got this little guy walking along the x-axis. Right now, the graph is below the x-axis, so that's negative. So when he started this journey at negative infinity, it was in the negative part of the interval. So from negative infinity, and then this wall, so to speak, of when it changes from negative to positive, when he goes and hits that wall, that's when it changes. So that's when it stops being negative. So I'm going to say from negative infinity to 1, that's when it's a negative interval. Then if he jumps over the wall and he starts walking over here, now it's positive. And so we're going to say x is an element of, when it's positive, starting at 1, and it keeps being positive for the rest of the way, so until infinity. And so that's how you would do that. The third one, this is actually not linear or exponential. This is what we call a quadratic. And you will spend a lot of time looking at quadratics next year in secondary 2. But we just wanted to show you a different type of picture and how a lot of the features will be looked at the same. So the x-intercept with a quadratic, there's actually 2 x-intercepts usually. And so we're going to list both of them. So it's going to be negative 2, 0 and positive 2, 0. And like I've mentioned before, next year in secondary 2, you'll spend a lot more time looking at x-intercepts than we do here in secondary 1. The y-intercept, there's that 1, so that's going to be 0, negative 4. Okay, for B, where it says state whether the function is increasing, we're not going to do anything with that for a quadratic. And the reason is it's a little bit more complicated than the other types of graphs we've looked at. It's decreasing and then it starts increasing, and so we're just not going to look at that this year. Next year you'll talk more about that. Okay, the domain. Again, if you walk along the x-axis, if you look up far enough, there's something up there, and if you look down, whoops, keep looking down, then you're going to look up. And so your domain, and this is true for all quadratics, it's going to be from negative infinity to infinity. Okay, the range. Now quadratics don't have an asymptote because they don't approach something. They actually will touch it and then go back up. And so a quadratic, we would not call that an asymptote right there because it's not approaching and getting closer and closer. It just goes down, touches it, and then turns around. So there aren't actually any asymptotes, and so the range is starting at negative 4, and it's actually inclusive here because it touches negative 4. So we're going to do inclusive, negative 4 to infinity would be our range. So down there on G, where it asks about asymptotes, we're going to write none. You're not going to have very many questions that have to do with quadratics, but we wanted to show you something else. Okay, the positive part of the graph. Let me highlight. The positive part is going to be this part right here, and then this part right here. So there's 2 positive parts of the graph. And then the negative part will be down here. So when we're naming the intervals for the positive, again, think about your little person walking along the x-axis. From negative infinity until I get to right here, it's positive. So from negative infinity until negative 2, and from this point right here until I get to infinity. So from 2 to infinity is also positive. I probably should have done that in the green. Okay, the negative part of the graph, so this part, it's from the time you get negative 2 until you get to positive 2. So that's going to be x is an element of from negative 2 to positive 2. Now again, the reason we're not doing inclusive on that is because 2 and negative 2 are on the axis, so they're not positive or negative. Okay, so now the next thing is the interval part. So I'm going to erase this and give you a second to make sure you've got things written down. So we're going to ask you about 2 different intervals. So the first one is from negative 3 to 0. So here's negative 3, and here's 0. So I'm looking at this point to this point. So we're going to find the rate of change for those 2. So we're going to go down 1, 2, 3, 4, 5, 6, 7, 8. And then over 1, 2, 3. That cannot be reduced, and so it's just negative 8/3. Okay, the next interval we're going to look at is from positive 2 to positive 3. And so let me erase my mess here from this. Positive 2 to positive 3. Okay, so that one, it's going to be Actually, I'm just noticing that I think I counted wrong on this last interval. It's going down 9 over 3, and so that does reduce to -3. So my mistake, I apologize. Okay, so back to our new interval from 2 to 3. We're going to go from this point to this point. So I'm going to go up 1, 2, 3, 4, 5, and over 1. And so that's going to be 5 over 1 is just 5. Okay. All right, so the next thing that we're going to look at is we're going to look at how different changing numbers changes our graphs. So now we're kind of transitioning to back, we're going to look at some linear equations and graph them. And so first we're going to graph y equals 2x. And so as you know, that's plus 0 there. So we're going to start at 0, and we're going to go up 2 and over 1. So we're just graphing these linear equations like we've done a million times. And if you put a lot of dots there, then a straight edge isn't absolutely necessary. We're not doing systems of equations, so it's not crucial that we have exactly straight lines. Okay, now number 5, we're going to graph y equals 2x plus 3 on the same graph. So I'm going to do that with a different color so I can see the differences. So we're going to graph starting at positive 3, but it's going to have the same slope. Now we already know that if lines have the same slope, they're parallel. And so the question is, how did changing my y-intercept from 0 to 3 change the graph? So I'm kind of asking if I was to take this red and move it to the purple, what would I do? And basically, what we want you to see it, there's a couple ways you could look at this particular one, but in order to be consistent with all of the ways all of the graphs work, every single point on this red graph moves up 3 units, every single point. So every single point, it's kind of like an elevator came and just lifted it. And so it's going to go up 3 if you change the y-intercept plus 3. And so I've got a little bit of a mess there. I don't really want all of that stuff. Then the next thing that we want you to do is we're going to graph with a different color now. I'm going to graph on the same graph. I'm going to graph y equals 2x minus 4. So that one is going to start down here at -4. It is still going to have the same slope. So we're looking at 3 parallel lines. The differences are where they cross the x-axis or the y-axis, the y-intercept. So what we want you to see again is that when you change the y-intercept from 0 to -4, it takes every point on there and it drops it down by 4. So it's kind of like an elevator dropping. Okay, so it's going to go down by 4. All right, number 9, we're going to do a similar type of thing. Okay, but this time instead of changing the y-intercept, we're going to change the slope and think about how that changes. So the first one we're going to graph is the parent function y equals x. So that's got an intercept of 0, slope of 1. And so I'm going to graph that. Even without a straight edge, as long as you put enough points in there, you can probably get a fairly straight line. Okay, so that's my y equals x. Okay, and then number 10, it says graph y equals 3x on the same graph. So we still have an intercept of 0, but this time we're going to have a slope of 3. And so what we want you to see here is that if we change the slope, the intercept is still the same, but if we change the slope, it becomes steeper. Okay, so a steeper line. And so just changing this number from 1 to 3, that makes it steeper. And when I say be specific, what I'm looking for is 3 times as steep. So tell me how much steeper. So it's 3 times as steep. So if you think about, climbing up the hill, the green one certainly looks a lot easier than the red one. Okay, number 12, we're going to graph y equals 1/5 x. So again, the y-intercept is 0, but I'm going to go up 1 and over 5. That looks like the one I want to climb up. Okay, so we're going to have this not very steep line. Okay, so how did changing the slope from 1 that we had originally to 1/5 change the graph? The intercept is the same, but the slope is less steep. So how much less steep is it? We would say that it's 1/5 as steep. Okay, pause if you need to. Okay, now some just general questions. So 14, what will happen to a graph when you increase the y-intercept by 5 units? So think about what's going to happen and write it down. So I'm going to have you pause the video and answer 14 through 17. So what will happen? So predict what will happen and see if you can call it right. So go ahead and try that. Okay, if you increase the y-intercept by 5 units, the y-intercept changing moves it up or down. So since I'm changing it by 5, it's going to go up 5 units. When you decrease the y-intercept by 12, it's going to go down 12 units. What will happen to a graph when you increase the slope? It will get steeper. And what will happen when you decrease the slope? It will be less steep. Okay, we're going to do these two now before we do one last problem. So graph y equals 2/3 x. So intercept is 0, up 2 and over 3. You can pause the video if you need to. And then I'm going to use a different color. I'm going to graph the line y equals negative 2/3 x. So it's the same except it has a negative slope instead of a positive slope. So I'm going to go down 2 and over 3. Whoops, that's not very straight. Okay, so if I look at that, my question is, which line is steeper? Okay, so think about that. Which line is steeper? So if you were climbing up them, which one would be easier to climb? Okay, now, of course, it depends on your direction, right? Because if you're going, you know, this one, you're going uphill. Well, that's always harder than if you're going downhill. That's easier, but it's still steep. So if you're coming down a steep hill, it's kind of like, you know, you're running, they have the same steepness. Okay, now as far as explaining, it's just a matter of direction. Okay, they're still the same steepness because if you were taking the same green hill, if you were coming up it, wouldn't it be just as steep as the red one if you're going up? And so it's just a different direction. That's the only thing. But the steepness is actually the same. Okay, the last thing that we're going to do is we're going to do a quick story problem. And this one is Mackenzie is skydiving. And so just thinking about the situation here, if we have, you know, somebody jumping out of an airplane, that's my airplane. Okay, so if you jump out and you're going to, you know, free fall for a little bit, and then you're going to pull a parachute, and then you're going to float down to the ground. So when you pull the parachute, you're not going as fast. So you're going fast here, then you're going not as fast there to get to the ground, and so that's the point. So I don't know some things about what Mackenzie is doing, but I do know that 40 seconds after she pulls her parachute, so our time is starting right here when she pulls her parachute. So 40 seconds later, she is at 2,600 feet, and then 125 seconds from opening, she's 1,750 feet above the ground. And so I want to know, first of all, an equation in slope-intercept form. So if you think back to what we've done before, I may not know how fast she's going, and I may not know how high she was when she started, but I do know two pieces of information. I can write an ordered pair for the first situation for the first part of what they told me. And I can write another ordered pair for the second part of what they told me. Now remember, we have to know which one is the independent variable and which one's the dependent variable. So the independent variable is going to be the time. We've talked about before why that's so. So 40 seconds, she's going to be at 2,600 feet. And then at 125 seconds, she's going to be at 1,750 feet. So to write an equation, I would first need to find the slope. So 1,750 minus 2,600, or vice versa. So we're going to have the slope is equal to, we'll just do 2,600 minus 1,750 over 40 minus 125. Now you can hopefully see that that's going to be a negative slope, but it makes sense because she's coming down. And so I'm going to have negative 850, well, 850 over negative 85, which comes out to negative 10. That's my slope. So I can use my slope and one of my points to write the equation of the line. So I'll do y minus 1,750 is equal to negative 10 times x minus 125. So you can use your calculator, they're kind of big numbers. And so I'm going to have negative 10x plus 1250 plus 1750. I'm running out of space. Y is equal to negative 10x and then plus 3,000. So that's my equation for Mackenzie's jump. Okay, now thinking about what that means. How far above the ground is Mackenzie when she pulls her parachute? So at the beginning, when she first pulled her parachute, how high was she? So think about the part of the equation that tells us that. It's going to be 3,000 feet because that's the y-intercept. That's when time began for this problem. Okay, how fast is she falling after she pulls her parachute? So after she pulls her parachute, how many feet per second is she dropping? And that's what the slope tells us. It tells us the rate of change. So she's falling 10 feet per second. And so that's how fast she's going. So again, just going back to using our ordered pairs and writing equations of lines, that's something that we're still doing, and we're still looking at how each piece of the equation affects the graph.